Good evening and welcome to our show, Astronomy for Everyone. I'm your host this month, Kevin Medden, and our guest this evening is Steve Whitty. And Stephen, we're going to do something a little bit different this show. It's kind of like catching the folks up on some of the stories they may have missed, or some they may not even understand because they're kind of complicated.
Yeah, that's right. So a number of clubs have an In the News segment, and we've been doing it for years. There is enough news to do a show like this at least every week, maybe 2 or 3 times a week. There's an awful lot of material out there that comes out of the news feed.
And what's interesting, our very first topic is quite new to us because the images have only been released for a couple of weeks for all intents and purposes. But what's fascinating to me about this story, not only the telescope that took the picture, but what the picture actually is.
Yeah, that's right. So the picture is the very first picture of a black hole. Now, we're not talking about the accretion disk necessarily, we're talking about the black hole itself. So in this picture, the dark section in there, people are calling it the shadow of the black hole. There's an event horizon and it neither reflects nor emits light, so it's really, really dark. So this is something that you, in some sense, can't see, but the accretion disk around it shows the outlines of it. So there's a bunch of interesting things that you get here. But it's not an easy picture to take.
And this, to give people an idea about what black holes are, this was a theoretical prediction of Einstein, as I understand it?
Absolutely. It comes straight out of general relativity equations, so right around 1917.
So now, we say this picture was taken by the Event Horizon Telescope, but this isn't a telescope on a tripod or a telescope at some observatory. This is a little more complicated geometry than that.
Yeah, it's a little strange. So in 1999, there was a researcher who said, we ought to be able to, in the near term, take this picture of a black hole. So here's the problem. The event horizon is very small, and the one that we actually took, which is in the heart of M87, a galaxy about 50 million light years away, this event horizon is something like imaging an eraser head on the moon. It's really a hard thing to do. So to do that, you need a telescope that, so you can have an image that is sharper if you have a larger diameter aperture. And in order to do this picture, you have to have an aperture that is the size of the Earth. You have to have a telescope that is the diameter of the Earth. So to do that, we use radio telescopes, and we use several radio telescopes, in this case 8 of them. And you combine the data and you run it through a computer, first a correlator and then an image algorithm, and then you produce a picture. So the image data was taken in April 2017, and the actual image was released just a couple weeks ago in April of 2019. So
that's 2 years.
2 years to get the picture. So it's not just you get the picture, but you also have to do some cross-checks to make sure that the picture is right.
And just because we used radio telescopes, that doesn't mean that weather doesn't play an important role in getting these pictures, because if we don't have clear skies that's somewhere in this setup, it doesn't work, correct?
That's right, yeah. So, and clear skies means different things at different wavelengths. The millimeter wavelength telescopes, like the one in the Atacama Desert, the ALMA, yeah, and there's also one in Hawaii. These telescopes are very sensitive to water, so you can't have water droplets, you can't have haze even. They are quite high and they're in very dry places, but still, you had to have good weather for the various telescopes at all of the sites, and you had to have that more or less simultaneously. No, so there were attempts that were made before 2017 that failed because of weather.
Right.
But they didn't start with their first attempt with all 8 telescopes. They started with 2, and then they added a third, and they actually got an image of sorts with the third, but not like this. And then they added, and in 2017, they finally got everything to work.
So given the complexity of how this telescope works, can we expect more from it in the future, though? Because obviously you're not going to waste all this energy and time not to get something else out of it.
So there are 2 things that we want to do. One of the things is that we would like to do this exact picture again, that is this same black hole in M87, so that you can see how the black hole changes with time. This picture has a picture of a jet coming out of the black hole in M87, and so the jet is millions of light years long. It's really quite interesting. But anyway, so you want to see how the black hole changes with time. And the other thing that we want to do, and it's in some sense a harder thing to do even though it's closer, is we want to image the black hole at the center of the Milky Way galaxy. So the black hole in M87 is 6.5 billion solar masses. 6.5 billion stars went in, the size of the sun went into that black hole. At the center of the Milky Way, we have a black hole that is still supermassive, but it's only, 6 million, not billion, 6 million black holes. So it's 1,000 times less massive, which means that the event horizon is smaller. So even though it's closer, the event horizon is 1,000 times smaller, but also, a similar distance, proportion closer. So,
so this story obviously gets the tagline, "To be continued."
Yeah, certainly. So we want to do both of those things in the future.
And our next topic that we're going to discuss is what I like to call do-it-yourself science or do-it-yourself astronomy. There is a way for in our case, an amateur astronomer to get a hold of data sets and actually help the professional astronomers accomplish things.
That's right. So the story is about a project called Black Holes at Home. So this uses the BOINC distributed computing platform, which started with SETI at home. So there are a bunch of this or that at home projects that are involved. And what this project will do, because it hasn't been released as of the moment, there is a website, but the project itself hasn't been released. What they're going to do is they're going to show they're going to do simulations on your computer. So you contribute computing time on your computer, presumably when you're not using it, and the results get correlated back at the central location, wherever that is.
And to wrap up our discussion of black holes, our third story is about something called primordial black holes. And what I found interesting about this topic, I think of a black hole as something huge, but when you talk about this, it's amazingly small.
Yeah, they are in fact amazingly small. So primordial black holes were predicted by Stephen Hawking, and they have not as yet been really seriously detected. But somebody said, if there are primordial black holes, then if you take a bunch of pictures of the Andromeda galaxy, then you ought to have, with the predictions of the count that we think might have been produced in the early Big Bang, they might make stars get briefly brighter. So they had like 16,000 candidates, and they narrowed it down to 1. And from this, they can tell. It suggests that there shouldn't be more than 0.5% of the mass of the dark matter that we detect. Less than that could be these primordial black holes. So how small are they? They're the mass of a mountain, like Mount Everest. They're pretty heavy, but they are the size of a marble. They're a centimeter across or something. They're really pretty small.
Well, this is a really good place for us to take a break, and I'm going to send it over to Don here, who's going to tell us about Term of the Month. But before we do that, just a quick reminder, if you Want more information about some of the topics we are covering here? Send us an email, which will appear down below on your screen.
Thanks, Kevin. The term of the month is NASA website. If you're interested in finding out the latest in space-related news, check out this website. Once there, you'll find links to NASA Live, NASA TV, images and videos, the ISS, news releases, and more. There's even an FAQ section where you can, for instance, find out if NASA images are copyright-free. The answer is yes, they are, in the public domain, but not the logo and the seal. Term of the month, NASA website. Back to you, Kevin.
Welcome back to Astronomy for Everyone. I'm Kevin Medden, and my guest this evening is Stephen Whitty. And Stephen, our next story concerns brothers who happen to be twins and also happen to be astronauts. So what did NASA gather from this information about having one brother stay at home and the other travel in space for, I believe, close to a year or a little over a year?
Yep, absolutely. So Mark and Scott, so Mark had been in space before, but Scott was in space for a year. They're twin brothers, so their genetic codes are maybe not identical, but they're very, very close. They're about as close as you can get. So in addition to your genes, there's something called epigenetics, little methyl groups that are all over the code, and these little methyl groups can are used by the body to sort of fine-tune the genetic code for the current circumstances. So they'll turn off genes or turn on genes even in response to things that are happening right now. So when you go into space, these epigenetics, these methyl groups, change, and quite a few of them will change, and they can be measured in the lab. So the picture that we had is people on an airplane that is in a parabolic curved flight to simulate weightlessness. This guy up on the top, he's not falling, he's sort of floating there. And what they're doing is they're doing blood purification experiments to see how they would do that on the International Space Station.
And the nickname for this plane is the infamous Vomit Comet.
Absolutely, because it can be kind of tough on you. So Scott went up and on the International Space Station for over a year, and periodically he would take a blood sample, and that would get sent back to Earth whenever the supply system sent a capsule back to Earth. So there are several samples of his blood over the course of the year, and then when he gets on the ground, they do that again. And in the meantime, they're doing that with Mark, who's been on the ground the entire year. So at the end, they compare the beginning and the ending groups and the methyl groups, and so they can see what the effects are. So they know kind of what genes were switched on or switched off, and they know how many, and they also know the recovery time, because when Scott got to the ground, it was like 3 to 6 months later. They keep doing these tests, and he gets back to within 5% of normal compared to his brother, and compared to the way he was when he started. And the upshot is that being weightless in space doesn't have any really lingering, long lingering epigenetic effects on the astronaut. It has an immediate effect where the body is attempting to adapt to this weird thing, microgravity, and so on, but it doesn't have a really long-term effect, at least not a very large one.
And
so this is good news for a Mars
mission, correct?
Mars mission, which is a year each way. You only have a window of every 2 years to either go to Mars or come back to Mars with an efficient trip time.
And our next story takes us to the tiny little country in the Middle East called Israel, and their attempt to become a member of what I call the Big Boy Club, joining China, the U.S., and Russia as the three nations who have landed a vehicle on the moon.
Yeah, so they got a ride on a SpaceX Falcon 9, and they have a fairly small spacecraft, and they used extremely efficient, fuel-efficient trajectory getting out to the moon and back. So they expanded the orbit around the Earth until they got out toward the sort of the midway point, and then they come into the moon and they slow it down. So everything was going
really well.
Yeah, everything was going really good until they got very close to the moon. So they were in the landing phase, and for some reason the main engines cut out, and that's the last they heard of it. But it was already going down to the ground, so they know they crashed.
But the Prime Minister of Israel was so impressed with this attempt that this will be again a continuing story, because they will take another opportunity to do this.
Yeah, so this is certainly the cheapest moon mission of that type. China recently landed a couple rovers, one on the far side of the moon. But so this was a first attempt by Israel, and they came extremely close to success. We should note that the surveyor missions that were part of the precursors to Apollo, at least a couple of the surveyor missions also ended by crashing into the moon. So I think the Russians did that once too. So this is maybe not desirable, but this is at least has been common.
And coming up next is Mars, because no news update show about astronomy can skip the planet Mars, since we've sent such a large armada of various types of spacecraft to this fine planet.
Right, and so we have a number of orbiters, and we have the Curiosity rover currently as operational on Mars. And this story is about methane. Now, methane has, oddly enough, been detected on Mars from the ground on Earth. The Keck telescope, more than a decade ago, detected Mars. It was just amazing. But we have ExoMars, which has the highest precision methane detection, what would you call it, an instrument on the spacecraft. So that's in orbit. And we also have a really pretty decent methane detection instrument on the Curiosity rover. So at Mount Sharp, where the Curiosity rover is, the rover detected a methane spike, so it went way up for it. And within a day, the ExoMars mission also detected methane at that location.
And what's interesting, besides the fact that we've discovered the methane, is the fact that one is a European mission and one is a NASA-related mission, and the interconnectivity works beautifully on this.
Yes, it's seamless, really. So why are we interested in methane on Mars? Well, there are two places where, on Earth anyway, there are two sources of methane. One is geological, and the other is life. So, you think of cows on the moon, but cows on Mars anyway. But it's not.
Okay.
It wouldn't be cows. It would be probably life underground. The methane builds up, and then you have
a lot of teeny tiny creatures.
That's right, and then you would have seepage coming out, or you would have some geological process which involves water, as I understand it, and you would have the same thing. It would build up for a while, and then it would come out all at once. You'd have an outgassing. So one of those two things, and either one of those two things, in my opinion, is really exciting. So life on Mars would be exciting, because
right.
then we could potentially...
Life anywhere other than here would be exciting.
Yeah, so we could then look to see if it was life that was either the same as ours on Earth, or if it was, and therefore a same origin, or if it was clearly a different origin than life on Earth. Either one of those would tell us quite a bit about life in general. But having a geologically active Mars, I think, would also be exciting. We've been thinking of Mars as a red and dead planet for quite some time. The Pioneer mission didn't really see much more than craters. It kind of looked like the moon. So it would bring life back to Mars in a geological sense.
And our next story has something to do with that very dark subject known as dark matter, but it's also about galaxies that they've discovered that lack dark matter?
Yeah, so there's a kind of a weird instrument called the Dragonfly Telephoto Array. And this has some weird properties, and they were able to discover two very diffuse galaxies that were candidates for being galaxies that simply don't have any dark matter. So how would you know if a galaxy has dark matter or not? Well, in the 1930s, Fritz Zwicky found that the rotation rates of the stars in galaxies didn't match what he expected. He had no idea that there was dark matter, so he expected that the stars that were farther from the center would orbit slower than the stars at the center. But what he actually found is that the stars from the center all the way to the out rotate lockstep, just like they were attached to a vinyl record rotating on your turntable. And that's not what he expected, and so he wrote it up and said, look, there's this weird effect. And we began calling it dark matter in the 1960s for a very odd reason, which is people ignored Fritz Zwicky because they didn't like him. They didn't like him personally.
Well, right, because there's a whole controversy about Vera Rubin and how she made a discovery, and then the Zwicky family got upset because they were thinking she was trying to take credit from Fritz. And
well, what Vera really did was she took Fritz Zwicky's research and brought it back to life. By redoing the experiments, she was able to bring the story back, and people started actually paying attention to the 30-year-old science that Fritz had done. Now, not everything that Fritz had done was brilliant. He had successes and failures along the way.
like most scientists.
But in this case, dark matter turns out to be, it's got to be something. We can measure it in a lot of different places. But in this particular galaxy, by confirming it with the Keck telescope, there's an instrument that is really good at getting the velocities of stars for doing this rotation checking. They found that, these two galaxies really don't have a lot of dark matter. That's all there is to it.
Well, in the couple of minutes that we have left, and there's a few stories here that we haven't gotten to, okay, let's quickly cover magnetars and the importance of, I believe it's between merging neutron stars.
Yeah, two merging neutron stars, which we first detected with gravity, with LIGO, they can form what's called a magnetar, which is still a neutron star, but the magnetism on it is ridiculously powerful, it spins quickly, and the magnetism dies down pretty quickly. From the LIGO data, they found what the light curves should be for a magnetar, and they then looked through Chandra archive data,
Which is the X-ray telescope.
X-ray telescope, and they found some candidates.
Well, thank you for being here, Steve. It was very interesting. Obviously, there's a lot more stories, so this format of a program will be continued. And just a quick reminder, if you want more information about our show or anything that pertains to astronomy, check out the website. And now we're going to send it over to Don, and he's going to tell you what's up in the night sky for May 2019.
Thanks, Kevin. What's up for May 2019? On the 1st of May, the sun rises at 6:29 a.m. and sets at 8:32 p.m. But on the 31st, it rises precisely at 6 a.m. and sets at 9:02 p.m. All times are Eastern Daylight Time. For our moon, we start off on the 4th with it being in the new phase, first quarter on the 11th, full the 18th, and the last quarter falls on the 26th. On the 10th, an interesting occurrence. The moon will pass in front of the Beehive Cluster, also known as M44, in the constellation of Cancer, the Crab. Moving on to the planets. Mercury and Venus are both in Pisces in the morning sky 1 hour before sunrise. Mercury makes superior conjunction on the 21st. Mars, we can find it low in the western sky 1 hour after sunset. It's not very bright, only Mag 1.6, which makes it only slightly brighter than Polaris, which is at 2.0. On the 6th, Mars positions itself perfectly between the horn stars of Taurus the Bull. Also on the 6th, in Taurus, the waxing crescent moon positions itself right above the Hyades, which form the face of the constellation. Moving on to Jupiter and Saturn, looking south 2 hours before sunrise, it's a really nice picture to take a look at. Add with that Antares, the brightest star in Scorpius, it makes a really nice view. Now Aries is down and to the right from Jupiter. Now both planets reach opposition 2 months later, so in July, so this will make for some great summertime viewing. And finally, the Eta Aquarids meteor shower peaks on the 6th in a moonless night. There's a maximum expected of 40 meteors per hour, and they're best seen beginning after 2:30 a.m. And that's what's up for May 2019. Keep looking up. It is, after all, the best free show in the universe.